This is the second revision video on vectors, and in this video we look at the equation of a plane and some further distance and angle results which relate to planes. So specification requires us to be able to find the vector and Cartesian forms of the equation of a plane, which will involve using scalar products. We need to be able to calculate the angle between two planes and also the angle between a line and a plane. We need to be able to find the intersection of a line and a plane, and we need to be able to calculate the perpendicular distance from a point to a plane. So looking at the key concepts and the key facts, if we have a plane, then there is always going to be a normal vector, which we will keep the letter n for, which is normal or right angles to all vectors that actually lie on the plane. So if A is a known point on the plane and P is any other point on the plane, then the vector joining A to P will lie on the plane. So the vector A to P must be perpendicular to n, which means the scalar product of AP with n must equal 0. The movement from A to P can be described in terms of the position vectors of A and P. To move from A to P, we need first of all to go from A to O, which is minus A, little a. That's the negative of the position vector of A. And having gone from A to O, we then need to go from O to P. And if we call little r the position vector of this general point P, then O to P is little r. So we know that A to P is the same thing as minus A plus r. So the fact that AP dot n equals 0 tells me that the scalar product of minus A plus r with n must equal 0. Multiply the brackets out, we get minus A dot n plus r dot n must equal 0. In other words, r dot n must equal A dot n. So wherever the point P is on the plane, the value of r dot n is going to be the same as the value of A dot n. In other words, we have r dot n is a constant for all points on the plane. And that's our vector format for the equation of a plane. If P has coordinates x, y, z, and the normal n is the vector n1, n2, n3, then we know that the position vector of P, that's the vector x, y, z, dot n1, n2, n3, must equal a constant. In other words, we know that n1x plus n2y plus n3z must equal a constant. And this is the Cartesian equation of a plane. And as long as we know one point on the plane and the normal of the plane, then we can work out the value of that constant. For the angle between a line and a plane, it's a really good idea just to draw a quick sketch diagram to represent what's going on. With that quick sketch diagram, one ought to be able to see fairly quickly that if one calculates the angle between the normal to the plane and the direction vector of the line, using the scalar product. That gives us the angle theta on the diagram. Then the angle between the line and the plane is simply 90 minus theta. So the strategy is to use the scalar product to find the acute angle between the direction vector of the line and the normal to the plane, and then the acute angle between the line and the plane is 90 minus theta. So we'll now move on and look at the angle between two planes. So in the two planes in the diagram, the angle that we have looking for is the angle theta. Thinking about the angle between the first plane and its normal, which is n1, and the angle between the second plane and its normal, which is n2, each of those two angles must be right angles, which means that the fourth angle in the quadrilateral that we have got must be 180 minus theta. Angles on a straight line then tell us that the angle between the two normals, or the acute angle between the two normals, must be equal to theta. So what we have got is that the acute angle between two planes is the same as the acute angle between the directions of the two normals. So to find the acute angle between two planes, we simply use the scalar product to find the acute angle between the normal vectors of the two planes. The acute angle between the normal vectors of the two planes is the same as the acute angle between the two planes. And finally, we've got the distance of a point from a plane and the perpendicular distance of the point alpha beta gamma from the plane with the equation m1x plus n2y plus n3z equals k is given by the formula the perpendicular distance equals the modulus of m1 alpha plus n2 beta plus n3 gamma minus k divided by the square root of m1 squared plus n2 squared plus n3 squared. Unfortunately, this formula is contained within the WJEC formula booklet, which you will have a copy of in the examination. Okay, so for our first example then, we have the point A with coordinates 3, 0, minus 2 lies on the plane which has a normal of 3, 4, minus 2. We have to start by obtaining the Cartesian equation of this plane. So, we know that the equation of a plane takes the form r dot n equals a constant. So we've got r dot 3, 4, minus 2 must equal a constant. We do know, though, that the point 3, 0, minus 2 lies on the plane. So the value of the constant can be worked out by just evaluating 3, 0, minus 2, scalar producted with 3, 4, minus 2. So the scalar product just gives me 9 plus 0 plus 4, which is 13. So we know the value of the constant is 13. So we know the equation of the plane is r dot 3, 4, minus 2 equals 13. And that is the vector form for the equation. We are asked for the Cartesian form. So we've just got to remember that the vector r is the position vector of a general point on the plane. In other words, the point x, y, z. So we've got x, y, z dot 3, 4, minus 2 equals 13. In other words, 3x plus 4y minus 2z equals 13 as the Cartesian equation of the plane. Moving on to part B, we have to find the perpendicular distance of the point 5, 1, minus 1 from the plane. And at this stage we've got the formula, which is in the formula booklet. So we've got n1 is 3, n2 is 4, n3 is minus 2, and we've got alpha is 5, beta is 1, and gamma is minus 1. So we just need to insert those values into the formula, and we obtain the perpendicular distance is 3 times 5 plus 4 times minus 1, 4 times 1 plus minus 2 times minus 1, take away 13, divided by the square root of 3 squared plus 4 squared plus minus 2 squared, which gives me 8 over root 29, or 8 root 29 over 29. Part C, we need to find the acute angle between the two planes. Now, the acute angle between two planes is the same as the acute angle between the two normals. So, the normal for the first plane is the vector 3, 4, minus 2. The normal for the second plane is the vector 1, 2, 1. So we are simply looking to calculate the angle, the acute angle, between the vectors 3, 4, minus 2 and 1, 2, 1. So using the scalar product, we have 3, 4, minus 2 dot 1, 2, 1 is the same thing as 3 times 1 plus 4 times 2 plus minus 2 times 1. So that is 3 plus 8 plus minus 2, or in other words, it's 9. But that is also the length of the first vector, which is the square root of 3 squared plus 4 squared plus minus 2 squared, times the length of the second vector, which is the square root of 1 squared plus 2 squared plus 1 squared, times by the cosine of the angle between the two vectors. So simplifying the left-hand side and the far right-hand side of that equation, we have 9 equals the square root of 29 times by the square root of 6 times cos theta. So we have cos theta equals 9 divided by root 29 root 6. So the acute angle between the two normals is 46.98 degrees, and we know that the acute angle between the two normals is the same thing as the acute angle between the two planes. So let's now move on to a second example. We have the points A, B and C, where A is 1, 2, 5, B is 3, 2, 7, and C is 4, 1, minus 2, lie on a plane. And we first of all got to show that the vector I plus 10j minus k is perpendicular to AB and AC. Now again, we need to just remember that I is a shorthand for 1, 0, 0, j is a shorthand for 0, 1, 0, and k is a shorthand for the vector 0, 0, 1. Okay, so we need to start by working out the vector A to B, and the vector A to B has a movement of 2 in the x direction, 0 in the y direction, and 2 in the z direction. So A to B is the vector 2, 0, 2, and if we wish to show that A to B is perpendicular to the vector n, then we need to consider the scalar product of AB with n. So the scalar product of AB with n is the scalar product 2, 0, 2 dot 1, 10 minus 1, which gives me 2 plus 0 plus minus 2, which gives me 0, which tells me that because the scalar product of AB and n is equal to 0, then the vector AB must be perpendicular to the vector n. In an entirely similar way, the vector A to C has an x movement of 3, a y movement of -1, and a z movement of -7. And the scalar product of AC with n is 3 minus 1 minus 7 dot 1 10 minus 1, which gives me 3, add minus 10, add 7, which again comes out to 0. So I know that the vector A to C is also perpendicular to n. Now this tells me that n is a candidate for being the normal to the plane. So we know that the normal to the plane is 110 minus 1. So I can say that the equation of the plane has got to be of the format r dot 110 minus 1 equals a constant. I know that A lies on the plane, so we can work the value of the constant out now very quickly. So we've got the constant must be the value of the position vector of A, 1, 2, 5, dot the normal, 110 minus 1, which gives me 1 plus 20 plus minus 5. So 1 plus 20 is 21, plus minus 5 gives me 16. So the value of the constant is 16. So we know the equation of the plane is r dot 110 minus 1 equals 16. And remembering that r is simply the position vector of a general point, in other words the position vector of the point x, y, z, we've got x, y, z dot 110 minus 1 equals 16, or x plus 10y minus z equals 16. Now we've got to find the point of intersection of the line and the plane. Now we know that the line has got the equation given above, and we've found that the equation of the plane is r dot 110 minus 1 equals 16. And we've got a pair of simultaneous equations there that need to be solved. If we substitute for r in the second equation, then we have 11 plus s, 2 plus s, minus 9 plus 3s. That's the format of r from the first equation. We're substituting it into the second equation, so that scalar product with 110 minus 1 must equal 16. So that means we have got, when we work out the scalar product, we've got one lot of 11 plus s, we've got 10 lots of 2 plus s, and minus 1 lot of minus 9 plus 3s must equal 16. Tidy that up, it becomes 40 plus 8s equals 16. So 8s must be minus 24 and s must be minus 3. Now that we know that s equals minus 3, we can find out what r is by substituting s equals minus 3 into the equation for L. So if I substitute s equals minus 3, I'm going to get the x coordinate is 11 plus s, so that's 11 plus minus 3, which is 8. The y coordinate is 2 plus s, so that's 2 plus minus 3, which is minus 1. And the z coordinate is minus 9 plus 3s, so that's minus 9 plus minus 3 times 3, so that's minus 9 plus another minus 9, which is minus 18 for the z coordinate. Finally, we need to find the angle between the line and the plane. And this is where this useful quick little diagram will remind us that the angle between the line and the plane is actually 90 minus theta, where theta is the acute angle between the normal and the direction vector of the line. So we're going to calculate first the acute angle between the normal and the direction vector of the line. And we're going to do that using the scalar product again. So the direction vector of the line is 113. The normal to the plane is 110 minus 1. We can calculate that scalar product very easily. 1 times 1 plus 1 times 10 plus 3 times minus 1 gives me 8. And that must be equal to the length of 113, which is the square root of 1 squared plus 1 squared plus 3 squared, times by the length of 110 minus 1, which is the square root of 1 squared plus 10 squared plus minus 1 squared, times by cos theta. So we've got 8 is root 11 times root 102 times cos theta. So cos theta must be 8 divided by root 11, root 102. So we've got the acute angle between the normal and the direction vector of the line is 76.18 degrees. So the required angle is 90 minus theta, which is 13.82 degrees. Our final example has point A with coordinates 5, 1, 2, lies on a plane which has normal 2, 1, minus 2. We've got to obtain the Cartesian equation of the plane, and then we've got to find the image of a point B after it is reflected in the plane. So we'll start off with part A, which is very similar to work that we've done already in this revision video. So we know that the equation of the plane must be of the form r dot 2, 1, minus 2 equals a constant. Since A is on the plane, we know the value of the constant must be 512 dot 2, 1, minus 2, which is 10 plus 1 plus minus 4, which is 7. So the equation of the plane must be r dot 2, 1, minus 2 equals 7, and the Cartesian equation is 2x plus y minus 2z equals 7. For part B, it really is a good idea to draw a sketch diagram, try and see what's going on. So we've got the plane, we've got the point B, and we are trying to find the image of the point B after a reflection in the plane. So we can add our onto our diagram a rough guess of where we think the image B' is going to be. And the key observation is that the line B to B' must be a normal to the mirror. In other words, B to B' must be parallel to the normal vector. Now that means that we know a lot about the line joining B to B'. We know that the line B to B' it has a direction vector which is parallel to the normal. In other words, we can use the normal as a direction vector for the line B to B'. We also know that the line B to B dash passes through B. So we know that the line B to B dash has got equation R equals 7, 5 minus 3. That's the coordinates of B, plus a parameter, t, times a direction vector for the line, and we've commented that we know that we can use n as a direction vector for the line. Now we can use our previous work to find the point where the line B to B dash meets the plane. We're calling that Q on the diagram that we've got. And once we've found the point Q, we know that B to B dash is just going to be twice the movement of B to Q. So the essence of this is now to find the point Q. So to find the point Q, we need the point of intersection of the line BB dash with the plane. So exactly the same as in the previous example, we substitute the form for R from the line equation into the plane equation. So from the line equation we can say that R is 7 plus 2t, 5 plus t, minus 3, minus 2t. And the scalar product of that with 2, 1 minus 2 must equal 7. So that's 2 times 7 plus 2t, plus 1 times 5 plus t, plus minus 2 times minus 3 minus 2t must equal 7. Tidy up the left-hand side of that, we get 25 plus 9t equals 7. In other words, we get 9t equals minus 18. So t must be minus 2. And if we take t equals minus 2 and substitute that back into the line equation to find q, then the x-coordinate of q must be 7 plus 2 lots of t. So that's 7 plus 2 times minus 2, which is 3. 5 plus t is 5 plus minus 2, which is 3. So the y-coordinate of q is 3. And the z-coordinate of q is going to be minus 3 plus t times minus 2. So that's minus 3 plus minus 2 times minus 2. So that's minus 3 plus 4, which is 1. So the point Q has got coordinates 3, 3, 1. To finish the question off, we now simply need to make the comment that the movement from B to B dash is twice the movement from B to Q. The movement from B to Q, well, in the x direction we start at 7 and we finish at 3, so that's a movement of minus 4 in the x direction. Start at 5, end up at 3 is a movement of minus 2 in the y direction. Start at minus 3, end up at 1 is a movement of 4 in the z direction. So we know the vector B to Q is minus 4, minus 2, 4. So the movement from B to B dash is minus 8 in the x direction, minus 4 in the y direction, and 8 in the z direction. We know that B is the point 7, 5, minus 3. So starting at 7, moving minus 8 tells me that the x-coordinate of B dash must be minus 1. Starting at 5 and then moving minus 4 tells me the y-coordinate of B dash must be 1. Starting at minus 3, moving 8 in the z direction tells me the z coordinate of b' must be 5. It is worth noticing how important a clear diagram was when we were trying to devise a route for finding the image of the point B' when the point B was reflected in the plane pi.